Everyone, it's October 5th. Finally, I finished reading the paper that has been bogged me down for so long. It took 3 days, a full 3 days of efforts to finally get down almost every small details of the paper. I mean, there's a lot of math in there, and there's a certain level of rigor that I want to go into this. I mean, is it possible that I prove every single one of them? No. But there is got to be a certain level, like in the paper, if they claim something happens, right? I don't want just to believe from this source. I want to see, okay, maybe somebody else have this theorem, or somebody else has a claim in other paper. So I want to see it. I want to see how everything got derived, not necessarily proven by myself. So finally, I think all the pieces are put together, and I think I have a good understanding of the method. It's some type of kernel learning, right? Some type of kernel learning for transfer learning. So it's not, I mean, it is complex, but on the other hand, it's not a black box. Like we know exactly what we're doing. The base is always convex optimization. And then, but they are very smart to turn the problem. I mean, the original way is indeed to learn a kernel, right? Actually, to learn a kernel embedding using semi-definite programming, which is very time-consuming. But then they changed it. They attacked it from a different angle, and now it's just icon decomposition, so it's much easier. So I'm going to use that. So tomorrow, I'm going to apply that to my data set and see what we get. Anyway, let's head on today's challenge. And also, if we get it done fast, we're going to revisit this thing, which we have an idea how to do it yesterday. So I'm going to do this later, hopefully. Okay, let's see this one. Time-based key value stores. Design a time-based key value data structure that can store multiple values for the same key at different timestamp and retrieve the key value, the key's value at a certain timestamp. Implement this time map. Set a key, a value, and a timestamp. Get a key and timestamp returns a value. Okay, store the key with a value at a given timestamp. Return a value such that set was called previously with timestamp pre smaller equal to timestamp. If there are multiple such values, it returns the value associated with the largest timestamp. If there are no values, return. So apparently this is going to be a heap, right? It's going to be a heap, and the timestamp is going to be the value, and then we're going to do negative in it. So let's say set full bar 1. So the key is full, the value is bar, timestamp is 1, and then get 1, we shall get bar out. Get again, timestamp 3. Hold on. No, I think that's a set. Alright, I'm back. Hold on. Set get, the second get. This get a bar. Set full bar 2 at timestamp 4. We get timestamp 4. Yeah, doesn't make sense. Okay. The key, because it's a lowercase timestamp, all the timestamps are strictly increasing. Hold on. All the timestamps of set, all the timestamps of set are strictly increasing. Then we, Wait, hold on. All the timestamp set are strictly increasing. For the get, I can get something smaller. Oh no, that's not a heap, because I need this to be smaller than timestamp, which means a timestamp going in the middle. So it's a binary search, right? It's a binary search, and since we are saying the set are strictly increasing, so we don't even have to sort. We'll just push it in the binary search. Okay. Let's see, binary search. See if it works. All right, so do you want default dict? Yeah, let's default dict this thing. So self dot m equals default dict a list, right? Set self dot m key dot append timestamp value, and then we need two binary search. Okay. Then we just say index equals. Hold on. When do we return empty? Largest if there are no values. Right, there's no values. Which means if it's 0, right? Index equal to bisect right self dot m key timestamp. Right? When we say if index equal to 0, which means the timestamp is the earliest, there's nothing earlier than it, then we'll return empty string. Otherwise, we shall return something that's smaller or equal to, right? Smaller or equal to. Yeah, so it's just going to be index. It should be index. It should be self.m key index. Huh. What if it's too large? No, it's going to be index minus 1. Always index minus. Index is the last one, so index minus 1. And the value is going to be 1. Okay. We don't have 1. Oh, I have to go key. My bad. Okay. Yeah, I think we can do this. That's pretty much it. Yep. That's pretty much it. Well, you can do a lot with key. I think I wrote an article about how to use key. I can use this to do full binary search, full powered binary search. But I forgot. I think I have to reread that. Yeah. 01 for set, login for get. Binary search. Heap plus linear search. sorted map plus binary search. Array plus binary search. Oh, OL time to hash the string. To hash the string. I don't really consider that. Okay, that will be it. Okay, now let's do this. So we have an idea. So the ideal is we will get the number of set bits for each value and turn that into a list. Actually, no, turn that into a set, right? And then we'll sort them from small to large, and then we'll go from the smallest. And we know if we have n bits in num1, and we need to have at least k minus n in num2. So we binary search it, right? We binary search it for k minus n, right? And then we'll get the value. And then it has to be this or larger, right? This or larger will work. So we'll go through all of them. We need a count, so we need a accumulated, right? It's a sum, cumulative sum. So we know from this to the end how many there are, and they're all different. So we just go this pair with all of them, right? This pair with all of them. And because this pair with all of them, and this pair with all of them, this pair all of them, and then if we have something that's, can to itself, then we have to consider that separately. So yeah, so there are a couple of considerations that we had to handle, but I think fundamentally this one is not too hard. It just took a long time yesterday for me to figure out the method. Oh, I like this one because it's easy to set up test cases, and in fact, we can use a stupid, like this is the type of thing we can also use a stupid method, but it's guaranteed to work, right? So we can check both methods. But anyway, so here's what we do, right? Here's what we do. We want to counter it first. Okay, so we want to counter it first. We need a counter. Anyway, we need a counter. So with a counter, we can say counter equals counter nums, right? Hold on. Yeah, my cat just jumped into the sink, got her feet wet. Anyway, so that's that. And another thing we want is what should we call it? We need a default dict. We're gonna call it map. So bitmap, bitmap, set bit map. Okay, so that's going to be the default dict with set. So when they say for n in counter, all right. So basically, it's just the number. So what we want to do? Oh no, this could be counter as well. My bad. This is gonna be counter as well. I don't know what I was thinking. So set bit counter. Okay, I'm going to say num counter, set bit counter. So for none is set in counter. So for each one, we're going to find out number of set bits. How do we find out that? So we can go bin n. Yes, bin n is 0b something, right? Yeah, we'll just count one. This one dot count one. There we go. So we can say this dot count one. So set bit counter this plus equal 1, right? And we're gonna go through everything. Now what we're gonna do is we're gonna sort, right? We're gonna sort the count. So set bits, sorted set bit equals sorted set bit counter, right? And then we're going to say sum sort set bit count equal to accumulate. Oh, we need to accumulate it tools. Accumulate. So the list accumulate for sorted set bit. Sorted set bit. So S in sorted set bit and set bit counter S. Right. So now we have all these. Then we can go from the first, right? I'm going to say for first for S in sorted set bit. Okay. And now what do? We binary search. Okay, so we need binary search. So let's go from bisect import bisect. I'm actually going to go bisect left, and then we can just plus 1, right? So we're going to say index equals bisect left sorted set bit and k minus s, right? K minus s. It has to be larger equal to this. So if it's equal, we will go ahead. So we just need to go index plus 1, right? Index plus 1. And we have to say if index plus 1 is equal to length, that means we have nothing, right? And at this point, I think we need a result as well. Okay, okie dokie. So what we need to do is to find out the total number of counts from index towards the end, right? So it's going to be, I'm going to say if index is smaller, index, so if it's too big, right? If it's too big, it's going to be, if index is smaller than len, sorted set bit. No, index, it could be here. All right, what if it's by itself? Then we'll plus 1, right? So we'll always plus 1. Because, hold on, plus 1. If it's in between, it will be here. Hold on. So it's going to be here, right? So it's going to be indexed by itself. If it's equal, then you will insert in front, which is still indexed by itself. Actually, I need to double check. I haven't used, it's too much. Bisect left, we say 1, 2, 3, oh yeah, 1, 2, 3, 4, okay. Bisect left, full, let's see, 3. So it should be 0, 1, 2. Yes, 2. So it's just going to be index. So if index is smaller, then we have something to go for, right? But if it's equal to, it's going to be, yeah, if it's larger, then there's no way, right? There's no way. And if it's too small, which is fine, right? It's too small, it's fine. So we can just do this. Okay. Wait. Yes, so that's index, right? Then we say if index, if sorted set index, right, is equal to s, right? If the two are the same, so we're handling this thing as the same, then res plus equal to int num counter. Oh, I don't even know who's whom. Gosh, dang it. Oh no. Oh no. Oh no, I don't even know who's whom. Yeah, I need to know who's whom. Because there could be, oh my god. Yeah, I have to know who's whom because we can have the same value twice. My, so this one cannot be a counter. This does have to be a default int though. Has to be default this. So this dot add n. So I need to know, right? I need to know. Oh, it's actually not. It's gonna be. I think list will suffice. List will suffice. So I just append. I need to know. So it's set bit. So it's gonna be set bit. It's not set bit counter. So it'll be set bit map, right? And then yeah, we can sort this. It's fine. This just not gonna be map s. It can be for s in sorted bits. This is gonna be len this. Len this. It's the same. This is still the cumulative sum, which is fine. Sorted bits is fine. Bisect is fine. This is fine, right? And then we say if it's the same number, right? The sorted set bit, right? If the sorted set bit is equal to s. Now this was a little bit complicated. Let's dot, and then we say else. So if the index is not equal to s, which means the index points to a number of bits larger, so then I just need to count. Is everything in this? Oh, do I even do? Yes, so everything in this, the count, times the first count, plus the next count times first count, the next count. So it would be the first count times all added together. So res shall plus equal to I just call cum sum. Presum. So it shall be presum this minus presum index. Because we want to do index, so it has to be index minus 1. Now what if index is 0? Well, index is 0 means index is not going to be 0. Like when index is going to be 0, it's going to be in here. Okay? So it's not going to be hitting here because we're taking the exact. Oh, hold on. What the hell are you talking about? It can't be 0 because it's k minus s. So index. What if index is 0? It just means k minus s is very small. So everything, right? Everything can be fit to do this. When everything can be fit to do this, so we have to say here is going to be index is larger than 0 times this, and I'm going to int this thing. we int this thing, so index has to be larger than 0. If it's larger than 0, then we do index minus 1, right? We remove the thing before the index, so it's from index at the end. But if index is 0, we cannot do so, it's going to be 0. Yeah, so rest plus equal to this multiplied by the length of set bitmap s. That's what we're considering at the moment. Is current s, right? We have this number of counts, different values, and each one of them can be multiplied by everybody else. So that's that. So we have to handle here now. So how do we handle this? Well, we have to handle this by, holy crap. Let's see, if it's equal to s, right? So we're saying that we can use just the same thing. So we can do combination, right? Combination first, which is C something, choose 2. So we add that, so we have the combination. So first is combination. Ooh, combination within themselves. Combination within themselves, and I need, is it combination or is it permutation? I think it's permutation, because 1, 2, and 2, 1 is different, right? Yeah, 1, 2, and 2, 1 is different, so it's permutation. What's the permutation? Isn't that n permute 2 is going to be n factorial divided by 2 factorial, right? Are you kidding me? N factorial. I don't think so. Wait, hold on. Permutation. I forgot a formula. What's the permutation formula? It shall be no, it should be n times n minus 1. That's what I think. Yes, just because n minus 2, so n times n minus 1. That's it. Yeah, because it's combination times the permutation part. Like combination is divided by r permutation. Yeah, so it's actually permutation, right? It should be permutation of all pairs within set bit map s. Okay, so rest plus equal to. I could have just set this one up. Index c equals this, right? So this one we just multiply by c, and this is just going to be c times c minus 1, right? That's permutation. And then after that, we're going to consider same value repeated, right? Same value in set bit repeats itself, right? Repeats itself. So for this, we have to go through them. Maybe there's a smarter way. So for s, I know I have this much, right? So for each number, I append that. because I don't want to go through everyone here. If I can know immediately which one has doubles, God, which one has double? Now which one has double? Like how many of them has at least 2 or more, right? That's enough, because if I have 2 or more, we just add that many. So maybe what we can do is the map, we can append something different. If I can do not the n, what's the point of append n? We shall append the count. I want to append hold on. So for the set bit map, right, I want to append for each value, I need to append hold on. All right, I just want to pre-compute everything. What am I doing here? Right? What am I doing here? How about lambda 0, 0? Okay, so we can say it's going to be number of values that has this number of bits, and the second one is a number of values that have at least 2 occurrences. So I kind of pre-computed here, right? And then it's not going to be a count. So we're going to say this is going to be your, what should we call it? We'll call it temp equals this, but we don't append, we don't do anything, right? And we say temp 0 plus equal 1, temp 1 plus equal to num counter n is larger than 1, and we're going to int this thing, okay? And then we have sorted the set bit, and we have pre-sum accumulate, and that's not the len. It's just going to be this 0, right? So this is the count of the number, right? Number of value that has this number of bits, the value that have at least 2 occurrences under this bit, right? Occurrences under the current number of bits, yeah, set bits. Okay, so if that's the case, right, then C is just going to be this 0. This is going to be C, right? This is the count. I have this in the same value. All we need to do is res plus equal to set bit map S1, because these are the number of values in this that has repeated itself. Because it's repeated, we can capture an additional result. And after that, we handle this, we can do index plus equal 1. because we've done this, right? And next will just be everybody else. And when we do this, we don't need to do else. We can just do this because the index it matches. And yeah, this is if it's larger, then we don't do it. So we go blah blah blah. Once we're done, then we just return the result. All right, it's time to check. Okay, we have a couple of simple tests. So this should be 5. And this shall be 10. Wait, 10. This should be 0. Oof. Let's see. This is 0. All right. It's going to be nums and k. Nums and k. There's going to be count. Try it. Okay, these two pass. Let's run a more comprehensive setup. Random import randint. All right. So how many test cases? 10 test cases. We need to print. Actually, this is a good test case. We can try this one. We need to print. First is going to be, let's say, 10. Print. Okay. For this in range 10. And we're going to say randint from 1 to, I don't know, 1 to, let's say 1 to 100. Okay. Then I'm going to print k. K randint 1 to 60. 1 to 20. Alright, so this is kind of our tests for now. Try it. We have a lot of things not right. Okay, let's reduce it down. Reduce it down to 10, and let's do 5, and let's go 10 as well. Huh, I thought we hit it in the first shot. Nope. All right, the first one is not right. Okay, let's handle this. First one, we have 6, 10, 7, 10, and 10. Okay, that's 3. Answer should be 9, but our answer is 8. Okay. All right, let's see why this one is not right. I kind of want to, let's see, let's print num counter set bitmap preset. Okay, let's check. Does see if it makes sense. So we have 10 3 times, 6 1 times, 7 1 times. Yep, that's correct. And I need to know 10 having 2, right? So 10 having 2, 6 and 7. 6 have 2. 7 has 3. I know it's 1 1 1. Okay. So now for the 2, I have 2 counts, 6 and 10, and one of them is more than 1. Yes. For 3, we have 1 count, and 0 of them is more than 1. That's also correct. So cumulative sum is going to be 2 and 3. That's correct. Okay. So number of pairs, right? We want it to be 3. We want it to be 3. So we have 2 and 3. So we go with 2, right? And so if it's 2, we can have 10, right? We have 10 or 6. So we have 10, 10, right? 10, 10, 10, 6, 6, 10. That's all 2 by itself. And then it could be 10 and 7, right? 10 and 7. And 7 and 10. 6 and 7. 7 and 6. So 1, 2, 3, 4, 5, 6, 7. Answer is 9. Wait, what did I miss? What did I miss? Oh, hold on. Oh, it doesn't matter. It doesn't matter if you repeat or not. My bad. It doesn't matter if you repeat or not. Dang it. It doesn't matter if you repeat or not. So we can have 6 and 6. Right? We can have 6, 6, and 7, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, yeah. So you don't have to repeat. I don't need this. Then this is going to be a counter. Easy peasy. It actually become easier, right? Become easier. Oh, hold on. Actually become easier. Set bit counter. Plus equal 1. Don't need any of this. This is just going to be this. And then rest. And then blah. C is going to be this. And then rest plus equal to this plus C. Permutation and the same number taken twice. And then we don't need this. Then we run. There we go. And it is actually C times C minus C plus. It is actually C squared. Here is actually C squared. We can just do C this. The expression is C times C minus 1 plus C equals C times C. For whatever reason, my cat just likes to go inside a cabinet. There's nothing we can do. Wrecking havoc inside. Yep. I think this time we got it. Now we can actually be more bold, right? Let's say 10, let's just say 100. We can do 1000, and this will be 0 to 60. We can actually be more bold. right? And then we copy and paste this whole thing, run it. I have to deal with my cat. Yeah, it passed. So, yeah, I think we submit it. Oh, we didn't test any. I think this should be right. There we go. Yeah, it's correct. Yeah, not the best time, but it's correct. Yeah. What would you say? It should be O n log n, right? This is a log n here, O n log n. Yeah. So the key, the breakthrough, right? The breakthrough is the realization that the number, the result of the total number of set bits from num1 and num2 plus num1 or num2 is the same as the sum of the set bits in num1 and num2. This is because any set bit that overlaps in the OR can be regained in AND, whereas any set bit that is cancelled, right? That does not overlap. And hence is cancelled in AND can be regained in OR. With this insight, we can build. Oh, then we don't even need num counters. Why do I even do num counters? I don't even use num counters. Yeah, you don't even use num counters. Come on, man. You don't even use num counters. You just need to use a set nums. Yeah, we just need set nums. With this insight, we can build a counter with the key being the number of set bits. We count the number of unique values in nums, right, that have the designated number of set bits. And we sort the keys, and we sort the keys for any key S. We binary search for where the binary search on k minus s to find from where the other number of set bits shall be for the other number. Alright, for the other number of set bits. And then to reduce computation time, we use prefix sum. Right? We use prefix sum to calculate, to make range sum calculation of 1. Now the last, then the number of choices, right? The number of choices is the number of, is the count of S multiplied by the count of all eligible bits. Count of all the other eligible number of set bits. The one complication happens when S can pair with S itself. Note that we don't have to, so here we have, here we have two possibilities. One is permutation of 2 among all the numbers that have S set bits. The other is each number pair with itself. Note that to pair, the number doesn't have to have more than one copy in the original nums. And that's that. Actually, I'll hold this and then I'm gonna submit this one to see if we remove we remove the counter. I think it might be faster. There we go. You don't need a counter. So yeah, it's going to be much faster. All right. Check discussion. Inclusion, exclusion principle. Yeah, that's that. Oh my God. Bit count. Oh wow. Times. Oh, yeah. Yep. But it's going to be O(n) squared. It could be O(n) squared. Mine is faster. Mine is faster. But the explanation is pretty bad. to find, I want to redo this. All the numbers that have set bits larger or equal to k minus s can be paired with s. Right. Kind of all the other unique, right? All the other unique numbers that have a number of set bits larger or equal to k minus s. Yeah, we don't have to do this. Yeah. Two positions, right? Two positions. Maybe we can combine these two, I don't know. Yeah, I think we can combine these two. Index, hold on. Let me think again. Yeah, index minus, I think we don't even need this. We don't even need this. We'll just do this directly. Yeah, I'll just say since s can be paired Yep. This also handles the situation where where sorted set bit index is equal to c, equal to s. Yeah, because it doesn't, I should say, note that since there is no requirement for a number to occur more than once in the original nums for it to pair with itself when k minus s is equal to s, and the rule of counting is the same as when k minus s is larger than s, is not equal to s. Yeah, so we reduce yet another one. So maybe we even Yeah. So all we need to do is this. Wait, do we have another? Yeah, we have another if statement. So we can reduce that if statement. So we have index, and this one we don't even need. We can just put it here. And we can just call this one counter now, because we only have one counter. Right? Counter. I mean, we can do counter like this. For n in set nums, counter like this. So I use this. I have sorted set bit, free sum, res, binary search. We do need this. And then okay. Let's see how long this one takes. Yeah, I think I might want to post this just for fun. Alright, let's produce another one. You know, just double check. Yeah. It's alright. It's the same. Okay, that'll be it for today. I think you did pretty well. I'll see you guys tomorrow.